Okay, guys, let's go ahead and get started. Exam 1 grades will be posted this evening on Blackboard, so be looking for those later today. All right, so today we're going to learn a new technique for proving propositional functions of positive energy. So this is called a mathematical induction. And so our goal in this technique is we want to prove statements of the form for all n with their positive integers, p of n. And so here, p of n is just a propositional function of n. N is some positive integer. Okay, so the way that this works is that this principle of mathematical induction. Okay. So to prove p of n for all positive integers n, we prove the following. Okay, so 1, and this is called your base case. We show p of 1 true. Okay. Now here, I should probably note, or wherever the statement starts. Sometimes the statement will start at like 2 instead of 1, or 0 instead of 1. But yeah, just the first in for which the statement is considering. And then 2, this is called your inductive step. Show P of k implies P of k plus 1 for all k for positive integers. Okay, and now here, this statement here in this conditional, this right here, this is called the inductive hypothesis. Okay. So why would this make sense? Well, these two steps are separate, but together they show that it's true for all n. But why? Well, if you show that the very first integer that you plug in, positive integer in the statement, if you show that that's true, that's part one, right? That's your base case. Then you just forget about your base case and you say, if you assume P of k is true, right? If you assume the statement is true for some integer k, and then that shows that the statement is true for the next integer, k plus 1, then together these cascade and show that the statement is true for every n. Because if that's true and that's true, right, so if both of those things are true, right, then P1 implies P of 2 is true. Because if that's true and that's true, then P2 must also be true. But if P2 is true, then that must mean that P3 is true. Because this statement here. But if P3 is true, then P4 must also be true. And this will go on forever for all positive integers k, provided that you've shown this part to be true. So together, these two things will show that a propositional function of n is true for all positive integers n. Okay? Now I think the best way to illustrate this is with an example. Okay, so the plane. So 1 plus 2 plus dot 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 plus n is equal to n times n plus 1 over 2. Okay? I like writing this using summation notation, so I'm going to rewrite it that way. The claim is that if you sum from I is equal 1 to n to I, that's equal to the closed formula of n plus 1 times n over 2. And it's the same statement. I just like using the summation notation when looking at these things. Okay, so proof. We'll say we will prove the claim by induction. Okay. So in order to do this, we just need to prove those two statements in the principle of mathematical induction. So first, we're going to show that the base case is satisfied. For our base case, observe that the sum of I is equal 1 to 1 to I. So we're taking n to be 1 here. That sum is just equal to 1, right? And this is equal to 1 times 1 plus 1 over 2. There. So everyone sees that this is if this is the propositional function of n, right? If you plug in a 1 on this side and a 1 on that side, they do equal. So you wouldn't write this in your proof, but just note for maybe your notes that i.e. p of 1 is true. You just verified that the very first instance of a positive integer of this propositional function, that very first instance is true. Okay? So next, we need to show, again, this isn't what you would write in blue. So anything I write in blue is not what you would write on your proof. This is just like for your notes. Next, we need to show pk implies pk plus 1. So that is, we assume p of k is true, and then show that p of k plus 1 is true. Okay, so this is our inductive hypothesis, as I mentioned before I erased. So next, for our inductive hypothesis, assume the sum of I is equal 1 to k of I is equal to k times k plus 1 over 2. So notice that's so p of k is what we assume, and we want to show p of k plus 1 is true. So we assume this is true, and then we want to show that this implies p of k plus 1. Okay? So then, if we look at the sum to k plus 1, right? So I is equal 1 to k plus 1. That's equal to the sum from I is equal 1 to k of I plus k plus 1. Okay. You see that this sum is equal to that right there. Okay. We're summing from I is equal 1 to k, and then if we add k plus 1, it's the same thing as saying from I is equal 1 to k plus 1, that sum. Okay. But by our inductive hypothesis, we know that the sum up to k is equal to that. Right? So normally I would write right here, but I'm running out of room, so I'm just going to write right here. So here, this piece right here is right here. Right? That's our inductive hypothesis, that that is equal to that. Okay? So then we just need to do some algebra here. So this is equal to k times k plus 1 plus 2 times k plus 1 over 2, which is equal to k plus 1 times k plus 1 plus 1 all over 2. So notice now what we've shown, right? What is p of k plus 1, right? So if I plug in k plus 1 for n up here, I get the following. So that's what p of k plus 1 is. So what we've shown here is that if we assume p of k, then this assumption implies that this here is equal to that, which is p of k plus 1. So then the next sentence would be something like, uh, hence we are done by induction, QED. Basically, once you show that, you're done. So honestly, I don't like the way that this looks right now. I don't think that it's clear enough for all of you. So I'm going to rewrite it. And this will happen a lot in your proofs courses. And the students that tend to be better will not only write a proof, but then look at the proof after the fact and decide if it's good enough, and then rewrite it until it's like the most clear and simple as you can possibly get it. So I'm going to do it again. And so I'm going to try my best to write out all the details though. The previous proof was okay, but I don't think it was the best. So proof, I'm going to say let p of n be the statement that the sum of I is equal 1 n equal to n times n plus 1 over 2. Okay. We will show for all n that are positive integers, even is true by induction. Or I'll go ahead and say by mathematical induction. Okay. So now There's a different style of doing proofs by induction that I'm going to switch to from the last style. Notice I indent a little bit, base case, underline. So observe P of 1 is a statement. The sum of I is equal 1 to 1 I is equal to 1 times 1 plus 1 over 2 is true. I know, observe P of 1 is a statement that which is true since both the left and right hand side of this equation equal 1. Okay. So then that proves the base case. So now we have our inductive step. Okay. Again, indented and underlined. So hopefully I have room here. I don't think I'm going to. For our inductive hypothesis, we assume UK holds for all positive integers k, i.e. that the sum of I is equal 1 to k of I is equal to k times k plus 1 over 2. Okay. So next, consider the sum see if I can do it here. So sum from I is equal 1 to k plus 1 of I, which is equal to the sum of I is equal 1 to k of I, and then plus k plus 1. I just like split this sum into up to k and then added the k plus 1 term there. But that piece right there, we know what that is equal to. It's equal to that by our inductive hypothesis. So typically, I would write this equation right here, right underneath there, but I ran out of room. And then with algebra, you can show that this is equal to a plus 1 times a plus 1 plus 1 all over 2. Really done. Okay, so we have our base case and our inductive step. Together, those show that that claim always holds. And again, if you think about it, the first one holds, good. And then if we assume P of K is true, then we get that, so maybe I could put like a comma here and say, then a period, hence P of K plus 1 is also true. And that would be because PK implies PK plus 1, right? So since P1 is true, then P2 is true, then P3 is true, so forth and so on. It's true for every positive integer n. Done. Okay? Any questions on that? Okay, so let's do another one. Okay, so let's see. Okay. So I think it says something like this. So claim so that the sum of I is equal 1 to n. Let's see. Of 2I minus 1 is equal to n squared. So the claim is that this formula always holds. And hopefully everyone here is comfortable with the summation notation. Right, this is just 2 times 1 minus 1 plus 2 times 2 minus 1 dot 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 plus 2 times n minus 1. So basically this is summing all the positive odd integers, right? Again, right, like this sum here is equal to, so 1 plus 3 plus 5 plus dot 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 plus 2n minus 1. And so when n is 1, that's equal to 1. When n is 2, we get that piece there. When n is 3, we get that piece. So it's just, you're summing these odd integers. And the claim is that that's equal to n squared. I actually didn't know that. I just haven't seen that formula before. But let's see if it's true. So proof Let's be very methodical like we were last time and write out every piece so that we understand what P of K is or P of N is. So let P of N be the statement. The sum up to N, 2I minus 1, I is equal to 1 to N, equal to N squared. We will prove for all positive integers n, P of n, by induction. Or mathematical induction, whichever you want to write. Okay? So once you say that we're going to prove it by induction, then you can go ahead and write your base case and your inductive step. So here, base case. We just have to show that P of 1 is true. So observe P of 1 is the statement. Sum I is equal 1 to 1. 2I minus 1 is equal to 1 squared. Which is true since both sides of this equation. So if we plug in a 1 for I, that's the only term here. So 2 times 1 minus 1 is 1, and 1 squared is 1. So since both sides of this equation equal 1. Okay. Right, so that proves our base case. Now our inductive step. So for our inductive hypothesis, we assume for all positive integers k, P of k, true, i.e. the P of k is the statement, the sum up to k is equal to k squared there, so i.e. The sum of I is equal 1k of 2I minus 1 is equal to k squared holds for all k that are positive integers. And now we need to show that under this assumption that P of k plus 1 is true. So So next, observe. It looks like I'm going to have enough room now. So we want to consider the statement P of k plus 1. Or we want to show that P of k plus 1 is true. So sum from I is equal to 1, k plus 1 of 2I minus 1 equal to sum from I is equal to 1 k 2I minus 1. So I'm just truncating this summation here. So I left out the k plus 1 term, so I got to add that back out here. Okay. So by inductive hypothesis, we know that this sum is equal to k squared. So actually, I would like it if you wrote that in your proofs. Something like by inductive hypothesis. We can replace that by that k squared. All right, so now we need to do some algebra here to get this to be k plus 1 in quantity all squared. So this kind of factoring out. So what is this? Oh, and this is k plus 1 squared. So this is the statement P of k, which is that equals to that, is true. P of k plus 1 is true. So hence, P of k plus 1 is also true. And we're done. Now, it's sometimes helpful for you to write out what P of k plus 1 is ahead of time so that you know where you're going, right? So I knew I could see it, but I'm not sure all of you could see it. That this statement right here is the statement that the sum from I is equal to 1 k plus 1 of 2I minus 1 is equal to k plus 1 squared. So that right there is the statement P of k plus 1. And we just showed that to be true. That is equal to that, because if we truncate this sum, we use the inductive hypothesis here to get that's k squared, do a little bit of algebra, it must hold. So for all k, P of k implies P of k plus 1. We're done. Okay? Any questions on that at all? Surely someone has to have a question. All right, so I guess we'll do another one. Okay, so the claim is that sum from I is equal 0 to n. So notice now we're starting at 0. Okay. 2 to the power I is equal to 2 to the power n plus 1 minus 1. Okay. Bring it into focus. Right, there it goes. So, and again, that sum right there, the summation notation, hopefully you're okay with it. But really what this is saying is, so this sum right here is saying 1 plus 2 plus 4 plus da 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 plus 2 to the power n. That's really what that sum is. And notice that we're starting with an index of 0 now. So we have a different starting variable. So proof. You'll probably guess what I'm going to write by now. So let Pn be the statement. The sum from I is equal to 0 to n. 2 to the power I is equal to 2 to the power n plus 1 minus 1. We prove P of n true for all non-negative integers n by induction. Okay, so once you state that you're going to prove it by induction, then I'm completely okay with you doing base case inductive step. Right? So, base case. We just have to show P of 0 is true. So observe P of 0 is the statement the sum of I is equal to 0 to 0 of 2 to the power I is equal to 2 to the power 0 plus 1 minus 1, which is true since both sides of this equation equal 1. Like 2 to the power 0 is 0. I mean, 2 to the power 0 is 1. 2 to the power 1 is just 2, and then minus 1 is 1. So both sides of that equation are 1. Since both sides of this equation equal 1. Okay, so that satisfies the base case. Now we move to our inductive step. Okay. So for our inductive hypothesis, we assume P of k true, i.e. So it seems like for k greater than or equal 0, i.e. The sum from I is equal 1 to k of 2I is equal to 2 to the power k plus 1 all minus 1 for k greater than or equal 0, something like that. Okay, so now we just need to show that P of k plus 1 is true. So next observe that the sum from I is equal 1 to k plus 1 of 2I is equal to the sum up to k, 2I, plus 2 to the power k plus 1. Right, is that sum. I just truncated this at the last term. Okay, so by inductive hypothesis, we can replace this by that. So I'm going to go ahead and drop that. That's just the index, right? Then you just erase the parentheses, I mean. So this is by inductive hypothesis. And that's equal to that. So now I can combine my terms. I have 2 to the power k plus 1 and 2 to the power k plus 1. Altogether, I have 2 of them. So I have 2 times 2 to the power k plus 1. And then that minus 1 is over here. These are right terms, so there's 2 of them. But now 2 times 2, though, it's the same base. So we can write this as, we increment the exponent by 1, right? So this is going to be equal to 2 times, 2 to the power k plus 1, and then plus 1, because same base, we add 1 to the exponent. And now this right here is the statement P, that equals to that is the statement P of k plus 1. So hence, P of k plus 1 is also true. And then we're done. Okay, so I'm going to post some extra problems for you to practice on on Blackboard, but that'll be it for today. I think I'm going to go ahead and start finishing up grading your exams, and I'm going to post those later to Blackboard. So hopefully by tonight you'll see your grade. All right, that'll be it. See y'all next time. Stay safe.